Hi, everybody. It's Professor Mitchell. We are going to get started today by looking at Chapter 1, An Introduction to Problem Solving. This chapter has two sections. The first section is on mathematics and problem solving. And in this section, we're going to be looking at the four-step problem solving process and then some examples of how to solve problems using various problem solving strategies. So the four-step problem solving process is number 1, understanding the problem. Number 2, devising a plan. Number 3, carrying out the plan. And number 4, looking back. So what does all that mean? Well, let's look at those in a little bit more detail. Understanding the problem means asking yourself, can the problem be stated differently? What is to be found or what is needed? What are the unknowns? What information is obtained from the problem? So what information is given? And what information, if any, is missing or not needed? In step 2, devising a plan, that means looking for a pattern, examining related problems and determining whether the same techniques applied to them can be applied to the current problem. That's a really important one. In other words, what have you learned from doing previous problems that seem kind of similar? Examine a simpler or special case of the problem to gain insight into the solution of the original problem. Make a table or list, identify a subgoal, make a diagram, use guess and check, work backward, or write an equation. And I want to stress that you will not use every single one of these in every problem. In step 3 of the four-step problem solving process, carrying out the plan, that means implement the strategy or strategies in step 2 and perform any necessary actions or computations. Attend to precision in language and mathematics used. So, try not to be sloppy or, as I sometimes say, phone it in. Do try to be careful with everything that you write. Check each step of the plan along the way. This may be intuitive checking or a formal proof of each step. Keep an accurate record of all work. That's so important. I had to learn that one the hard way, and maybe I'll tell you that story sometime. I used to hate showing my work when I was in school, and a few teachers had to get on my case about it, and eventually I realized that I would actually do better on my tests if I was a little bit more careful about showing my work. You're not just doing it for the teacher, you're also doing it for yourself. And finally, looking back. Check the results in the original problem. In some cases, but not too many in this class, this will require a proof. Interpret the solution in terms of the original problem. Does the answer make sense? Is it reasonable? And does it answer the question that was asked? I have a story that I love to tell. Many, many years ago, I was teaching a pre-calculus class. And one of the things that we learned how to do in that class was using latitude and longitude and knowing the radius of the Earth, you can approximate the distance between two cities that lie on the same line of longitude. So one time I gave a quiz that covered this topic, and I had a student make a really understandable mistake, but they came up with the distance from Dallas to Omaha was 5 million miles or something. And I think the person just wrote 5 million as the answer. And I like to think that if the person had written a complete sentence, the distance from Dallas to Omaha is 5 million miles, that might have triggered something, and this person might have gone back and checked their work. Oh yeah, I forgot to change degrees to radians. It turns out that was the mistake they made. Determine whether there is another method of finding the solution. That's one that I like to use sometimes. If I know two different ways to do the problem, I'll use the second way as a check to see if I get the same answer. And if possible, determine other related or more general problems for which the techniques will work. That's a really good one if you can get that to work. All right, strategies are tools that might be used to discover or construct the means to achieve a goal. Because problems may be solved in more than one way, there is no one best strategy to use. Sometimes strategies can be combined in order to solve a problem. All right, this is one of my favorite problems. It's a very famous problem, and they call it Gauss's problem here. Carl Gauss was a very famous mathematician. I believe he lived in the 1700s. And the story goes that when he was a child, his teacher was looking for some busy work for the class to do. And so the teacher asked the students to find the sum of the first 100 natural numbers. In other words, what is 1 plus 2 plus 3 plus 4, blah, 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 all the way up to 100. And in other versions of this story, I've heard Gauss was in something like first grade when this came up. So teacher thought this would keep the class busy for a while. However, Gauss gave the answer almost immediately. So let's look at how he did it. So remember that the natural numbers are the numbers that you used to count with. They're also sometimes called the counting numbers, 1, 2, 3, 4, et cetera, et cetera. And as I said a minute ago, the problem is to find the sum 1 plus 2 plus 3 all the way up to 100. So here is how Gauss did it. And in doing this, he discovered a formula for the sum of the first n natural numbers, which I'm going to share with you in a minute. So I want to talk you through this. If we call the answer S, S is the sum 1 plus 2 plus 3, blah, 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 up to 100. We'll write it here on this line. S equals 1 plus 2 plus 3 plus 4, blah, 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 up to 100. And then if we write those same numbers in reverse order, 100 down to 1, something kind of cool happens. If you line all these numbers up vertically, S plus S is 2S, 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, all the way down to 100 plus 1 is 101. So what we get out of this is that 2S is equal to 101 plus 101 plus 101, blah, 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 blah. And those numbers are being added together 100 times. You can see that by the way they're lined up under here, right? So that sum is 2 times our answer. So to get the answer, we just have to divide that sum by 2. So again, since there are 100 sums equal to 101, that means that 2S is equal to 100 times 101, and that means that S is equal to 100 times 101 divided by 2, which you can check works out to 5,050. So here's the formula, because we're going to use it again here in a little bit. The sum of the first n natural numbers is given by this formula. 1 plus 2 plus 3, blah, 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 all the way up to n is equal to n times n plus 1 divided by 2. So if you substitute 100 for n in this formula, the n is the 100, the n plus 1 is the 101. So it works out to 100 times 101 divided by 2. Now, I haven't really proven to you that that formula works for any value of n, and that's really not the kind of thing we do in this class, so just take my word for it. You have seen one example. It'll work for, I mean, even if you just use the unknown n, you can do this same kind of thing and it'll still work. All right, the method is mathematically correct because addition can be performed in any order. Remember, we wrote the sum first as 1 plus 2 plus blah, 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 up to 100. And then we wrote it again as 100 plus 99, blah, 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 down to 1. And multiplication is repeated addition. We rewrote 101 plus 101 plus 101, da, 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 100 times as 100 times 101. And the sum in each pair is always 101. I think this explanation is kind of making it more complicated than it really is. I mean, if it's clear to you that these pairs of numbers will always add up to 101, I think that's pretty clear, okay? But they wrote it very formally here. For example, they wrote 2 plus 99 as 1 plus 1 plus 100 minus 1, and then the ones cancel. All right. I think that's kind of maybe over-explaining it a little. All right, so here's an example. We're going to try to apply the trick that we just learned. So the problem is to find the sum of the even natural numbers less than or equal to 100. So in other words, find the sum 2 plus 4 plus 6 plus 8 all the way up to 100. Notice that the formula that we just developed won't work in this problem because that's only for the first n natural numbers. So it wouldn't work for just even numbers or just odd numbers. It has to be consecutive natural numbers. However, there's at least one way that you can make that formula work. This was not the first way that I thought of. So recognizing that the sum can be separated into two simpler parts relates to Gauss's original problem. And so what they did was they factored the number 2 out of every one of these terms. See, 2 is 2 times 1, and 4 is 2 times 2, and 6 is 2 times 3. So you can pull that 2 all the way out front, and it turns into 2 times 1 plus 2 plus 3, blah, 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 up to 50. And then you can use the formula that we just learned. So the sum of the first 50 natural numbers using that formula is 50 times 51 divided by 2. And you should double check, get out your calculator and double check that 2 times 50 times 51 divided by 2 works out to 2,550. This was actually the way that I thought of. A different way to approach the problem is to realize that there are 25 sums, each equal to 102. So notice if you pair the 2 with the 100, you get 102. If you pair 4 with 98, you get 102. If you pair 6 with 96, you get 102, et cetera, et cetera, et cetera. And there are 25 of those sums. Think about why that is. Why are there 25 of them? All right, and then 25 times 102 also comes out to be 2,550. One strategy for solving a complex problem is to examine a simpler case of the problem and then consider other parts of the complex problem. Another strategy often used is to make a table. A table can be used to look for patterns that emerge in the problem, which in turn can lead to a solution. All right, and then another one of the strategies that we notice, I'm not giving examples of every single one of these strategies. There are just too many. So what I suggest you do is go into your homework. I probably will throw in a few of these, different ones. I'll put in ones that I think you can handle. And always, 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 if you have any questions, post your questions in the discussion boards or send me a message. So an example of identifying a subgoal is a magic square. This is called a magic square. And the problem is to arrange the numbers 1 through 9 into this square, which is subdivided into 9 smaller squares, so that the sum of every row, column, and the main diagonal are all the same. Okay. So again, each of the nine numbers 1 through 9 must be placed in the cells, a different number in each cell, so that the sums of the numbers in each row, in each column, and in each of the two major diagonals, this one here, and also this one here, all of those sums have to come out to the same number. If we only knew what that fixed sum was, that would be really helpful. We would have a better idea of which numbers can appear together in a single row, column, or diagonal. So the sub-goal in this problem is to figure out what would that fixed sum be. And it turns out that's pretty easy. All right, if you added together all the numbers in the whole magic square, that's going to have to be 3 times the sum in one row, or one column, or one diagonal, right? And, oh, lucky us, we just figured out a way to add these numbers together, right, using that formula. The sum of the numbers 1 through 9 would be 9 times 10 divided by 2. 9 times 10 is 90. 90 divided by 2 is 45. All right, so that means that the fixed sum, each row, column, and diagonal has to add up to 15. And that's really, really helpful. Okay, so now we'll start thinking about what numbers could occupy the various squares. And we're going to start with the number in the center space. That number is going to appear in 4 different sums, each adding to 15. And we're talking about the 2 diagonals, the second row, and the second column. So what we're going to do is write down all the different ways to add 3 of these numbers, 1 through 9, and get 15 as the answer. And it turns out there aren't as many of those as you might think. So if we write 15 as a sum of 3 different numbers, 1 through 9, in all possible ways, we could then count how many sums contain each of the numbers 1 through 9. The numbers that appear in at least 4 sums are candidates for placement in the center square, whereas the numbers that appear in at least 3 sums are candidates for the corner squares. So here are all the different ways of writing 15 as the sum of 3 different numbers 1 through 9. You can see there aren't very many. Notice that the number 5 appears in 4 of them. So the number 5 has to go in the center square. And because the numbers 2, 4, 6, and 8 appear 3 times each, for example, there's 2, 1, 2, 3 times. Let's see, what else did they say? 4, 1, 2, 3. Yeah, so the numbers 2, 4, 6, and 8 have to go in the corner squares. All right, now if you imagine this square is all filled out, all right, and all the rows, columns, and diagonals add up to 15. If you then took that square and rotated it, it would still work. All right, so you can actually pick any one of these 4 numbers to go in, say, the top left corner. So let's say we decide to go with the 2. That means, because we know that this diagonal has to add up to 15, the 8 has to go in the opposite corner from the 2. Now, if we put 6 in the top right corner, that means that 4 has to go in the bottom left corner, and then it just kind of all falls into place, all right? Because, sorry, this thing kind of filled itself out pretty quickly. But if you imagine, you know, having the middle square and the 4 corners filled out, you could then fill in the rest of the numbers, because on these outside rows and columns, there would only be 1 number missing. Okay? So that's called a magic square. Looking back, we've seen that 5 was the only number among the given numbers that could appear in the center. However, we had various choices for a corner, and so it seems that the magic square we found is not the only one possible. Like I said, if you rotated it, 90 degrees, 180 degrees, it would still work. All right, here's an example of the strategy making a diagram. Bev and Jim ran a 50-meter race 3 times. The speed of the runners did not vary. In the first race, Jim was at the 45-meter mark when Bev crossed the finish line. So we have 2 questions about this. In the second race, Jim started 5 meters ahead of Bev, who started at the starting line. So the question is, who won that race? And in the third race, Jim started at the starting line, and Bev started 5 meters behind. Who will win that race? It almost sounds like B and A are the same thing, doesn't it? So let's see if they have the same answer. When Bev and Jim run a 50-meter race, Bev wins by 5 meters. That is, whenever Bev covers 50 meters, Jim covers 45 meters in the same amount of time. If Bev starts at the starting line and Jim is given a 5-meter head start, we're to determine who wins. All right, so let's focus on that for a second, and then the next question is down here at the bottom. All right, so here's a diagram of the first race. Bev ran 50 meters in the same amount of time that Jim ran 45 meters. So Bev won the first race. If Jim had a 5-meter head start, he would still cover 45 meters in the same amount of time that Bev covers 50. So in the second race is going to end in a tie if Jim is given a 5-meter head start. Now, where it really gets interesting is in the third race. All right, so remember in the third race, Jim started at the starting line. Here's the starting line right here. They didn't make this super clear. All right, and so again, Bev covers 50 meters in the same amount of time that Jim covers 45. So at the 45-meter mark, they're going to be tied. So the question is, what happens over those last 5 meters? Well, we know that since Bev can run 50 meters in the same amount of time Jim runs 45, that tells us that Bev runs faster than Jim. So if you give them the same amount of distance to cover, Bev is going to cover that distance just a little faster. All right, so in the first race, Bev wins by 5 meters. In the second race, they tie. But in the third race, Bev wins again because she covers the last 5 meters faster than Jim, and so she'll win the race. Looking back, the diagrams show the solution makes sense and is appropriate. All right, next strategy, work backward. In some problems, it is easier to start with the result and work backward. That is not cheating. So for example, it took workers 5 weeks to dig a 10-mile tunnel. During the 4th week, the workers dug 2.5 miles. The next week, they dug 1.25 miles to complete the tunnel. How much had the workers completed after the first 3 weeks of digging? This is a pretty easy problem, don't you think? All right, so it took them 5 weeks to complete the whole 10-mile tunnel. During week 4, they dug 2.5 miles. During week 5, they dug 1.25 miles. And we need to find out how many miles of tunnel they dug in the first 3 weeks. So the plan is to work backwards. We know how many miles they dug in the last 2 weeks. So we'll work backwards. In weeks 4 and 5, they dug a total of 3 3/4 miles, right? Because 2.5 plus 1.25 is 3 3/4. That means in weeks 1 through 3, they must have dug 10 minus 3 3/4, which is 6 1/4 miles. So in weeks 1 through 3, they dug a total of 6 1/4 miles. Looking back, that answer makes sense because 6 1/4 plus 2 1/2 plus 1 1/4 does come out to 10. All right, the guess and check strategy. First, guess at a solution using as reasonable a guess as possible. Then check to see whether the guess is correct. The next step is to learn as much as possible about the solution based on the guess before making a next guess. Sometimes when I teach algebra classes, I recommend this strategy. It's actually helpful. I mean, I hate the guess and check strategy for solving algebra problems, but it is sometimes helpful to come up with the equation that you're supposed to solve algebraically in order to get the answer. This strategy is often used when a student does not have the tools to solve the problem in a faster way. And they say here that that's primarily in grades 1 through 3. However, I have seen students in higher grades use guess and check. Really, it's appropriate in any situation where they haven't learned the faster way to do the problem. All right, and then finally, the write an equation strategy. Even though algebraic thinking is involved in the strategy writing an equation and may evoke thoughts of traditional algebra, a closer look reveals that algebraic thinking starts very early in student school lives. For example, finding the missing subtrahend in a problem like 14 minus blank equals 3. All right, that's an algebra problem, even though we don't call it an algebra problem in elementary school. And that's going to take care of section 1.1. We'll see you next time for 1.2.